Good morning, everyone. Thank you so much for joining us. We're really hoping that you learn something about circulation systems today, and yeah, look at solutions that will help with sustainability in the long term for your labs, for your applications, yeah, and work towards bettering the world. I'm Tamryn Lucas. I am the product manager here at Lasec for these circulation systems. I'm joined by Steve. He is the LAUDA specialist there at LAUDA for the closed loop systems. Steve has a lot of experience with these systems and within the field of circulation and chilling systems, both on the ground, working with the systems with customers, as well as more theoretical applications. So yeah, thank you again for taking the time out of your day to join. And without further ado, I'm going to hand over to Steve.
Thank you, Tamryn, and thank you for the audience here for joining us today. I'm pleased to have been invited along to discuss water sustainability and the theme that Lasec is promoting over the next several months with various topics, all discussing sustainability. Today, I'd like to introduce the use of temperature-controlled circulators, chillers, for replacing water from mains tap water, from bore water, and other uses to help meet sustainability targets. Of course, there's a great deal more to using chillers rather than only just sustainability. They provide clean, efficient, controlled solutions for the laboratory. So a little bit about LAUDA. Our headquarters are in LAUDA, Germany. LAUDA is the name of the town, and the company takes its name from the town. We have manufacturing there and across other sites within Germany. We also have manufacturing sites in the USA, Spain, and China. And having been established in 1956, we now have approximately 600 employees and a turnover of around 110 million euros. In the image there, we see the factory at LAUDA nestled in a quiet rural German countryside. LAUDA is recognized as a global market leader in temperature control systems and also maintains the silver top 15% in the world of companies meeting EcoVadis Silver Medal Award. This is a rating for sustainability for the company as a whole. Sustainability is important to LAUDA, and we endorse any company that is looking to improve sustainability for the future. So considering water usage, where do we use water for cooling in the laboratory? Well, there are a number of different applications, including analytical equipment such as mass spectrometers. These require continuous cooling for vacuum pumps and detector systems, as do NMR spectrophotometers, X-ray diffractometers, and electron microscopes. Now, we recognize that maybe you don't have any of these for yourself directly, but perhaps in your company as a whole, this equipment exists and consumes constantly some water, or perhaps it's already connected to some kind of water cooling system. In the general laboratory, for example, in chemistry, pharmaceutical, universities, we're probably familiar with water condensers. These are most often used to trap volatile solvents, maybe acetone, ethanol, toluene, and so on. We find condensers on top of reactors, reaction flasks, in use with rotary evaporators or other evaporating devices, and in distillation systems. They're also used to provide some level of cooling for other apparatus associated normally with heating. So, for example, some autoclaves, furnaces, ovens have a water supply to balance back against that heat that's being provided by the electrical heating. And that provides some fine control, particularly at the lower temperatures. Equipment such as lasers or equipment using lasers as part of their system often have a connection for a water cooling system, and vacuum pumps. Again, similarly, vacuum and temperature control go very much hand in hand. Typically, as I was mentioning, water condensers are very common. There are many different designs and types. I've put some of the more common designs here, and typically it's a coil of some kind connected to tap water, but often using barbs or perhaps GL14 connections. On the right of the screen, there's an image of a Soxhlet extraction system. Soxhlet, Keeldal, these systems are very common and often run in parallel, consuming huge amounts of water. And if they're running off the mains, that's a big demand on the water cooling system being supplied to the site. Rotary evaporators are very common, and to have them connected up to a cooling water system can present some issues which are overcome when using a chilled, temperature controlled water supply. Evaporators come in different sizes, from the benchtop through to kilo lab or plant size, which may have 2 or maybe even 3 condensers if there's a trap on the vacuum line to prevent reboiling. So when we consider water usage, what are the areas that we should think about change? Why move away from what we're all familiar with, using taps, faucets, running water, typically switching it on, turning it on, having that water running constantly, and it just going down the drain? Well, does the water temperature change? I've come across cases in the past where, for example, a university had its water tank on the roof in a big black box. And during the summer, the temperature of that water may get up to somewhere around 30, 35, 40 degrees centigrade. It was on the roof to be able to provide a head of pressure. And the university spoke with us regarding the temperature control, because at 40 degrees, the chemistry lab wasn't getting any cooling, and they needed to improve the cooling because there was a health and safety issue with not trapping the solvents that were escaping from reaction vessels. Unstable temperatures, inconsistent flow rates. If the flow rate is constantly changing, then the level of cooling that's being applied to a condenser will change. Why would a flow rate change? Well, perhaps there's other demand on the system. Maybe there's a machine nearby that is also using that water supply, and as the demand for that machine increases or decreases, then the flow rate changes. It could also change the pressure in the system. By changing the pressure, you may find that there's a back pressure on the tubes. So imagine here that we have the tap shown with barb connections. It's not uncommon for the pressure to, for example, increase and that pipe come off, and then the water is just left to run. Or perhaps it's at the application end. So maybe there's the chance of lab flooding. It occurs. It can happen. It's a known risk. And the building managers and the safety people are very aware of the risks of lab flooding. There was a case, again, in a different facility in Australia that I came across, where a lab flood in the chemistry lab actually ended up working its way downstairs to the computational chemistry lab, and that sadly destroyed all of the computers in that lab. So we need to think about what is the cost implication if these lab floods occur. We also need to have a water supply and a water drain, which may sound a fairly obvious statement. However, the reason that I mention it is there are projects that we work on for mobile laboratories. For example, a porta cabin kitted out with equipment for on-site analytical testing of soil, for example, or water analysis, environmental analysis. There is no water supply or drain, and by having a temperature controlled circulator or a chiller to provide that cooling water for the porter cabin lab is an important add-on to the facility there. Many companies globally may use well water or bore water to provide their cooling water. We would strongly recommend against this, as the impurities that would be in that water would be very damaging to any machine that they may have. We spoke earlier about the use of spectrophotometers of different types, and we would want to avoid long-term fouling or contamination of those water cooling systems inside that rather costly equipment, valuable equipment that provides an important service. If the maintenance of that equipment is not kept up and fouling occurs, then we're damaging those machines. Pressure I mentioned earlier, and can also come not only because of the demand on a particular supply at a particular time, but for example, we find often that the site water pressure will increase overnight as the demand generally drops. And if a flood is likely to occur, very often statistics show that it would typically happen overnight when there's nobody available to deal with that flood. Erratic and unreliable pressure has an influence on the temperature control as well, and the cooling effect of that condenser. And the main point here for this presentation is that it's wasteful. It's money down the drain. We're throwing water, this valuable resource, down the drain. So what are the benefits of using a chiller? It means that we get stable temperatures. We can dial in a temperature of, for example, 10 centigrade, 15 centigrade, and it will keep that temperature constant. That gives us repeatability, reproducibility, and constant cooling in our application. We have consistent flow rates, not influenced by whether it's daytime or nighttime or what other demands might be on the system. There's a very low risk of flooding. We acknowledge that, yes, a pipe may come off if it's not secured properly. However, it's only the contents of the chiller that could potentially leak, not a continuous flow from a mains water supply or from a cooling tower or from a larger system. We don't need to supply a water mains input and a water drain. It's not required, as we discussed with the porter cabin laboratory approach. We can use clean water or water glycol, and that clean water is going to protect and preserve our expensive NMR machines or spectrophotometers that we have, whatever we're connecting it to. And we have reliable and constant pressure. Again, it's consistency so that our results are consistent. And the big key point, it's more sustainable. We're not throwing water down the drain. So the comment that I get from many lab users is, yeah, Steve, this sounds great, but I don't have any budget for chillers. So while I love the idea of moving to chillers, I can't afford them. If I choose to buy some chillers, it will come from my laboratory budget for equipment. And I'm already strapped for that. I can't afford to be buying new equipment for this. We acknowledge this. And therefore, because the comment is that for the general lab chemist, the water is free, it's paid by the building management, we would recommend that you find out who is responsible for paying for the water supply for your laboratory. Who has the responsibility to reduce the mains water usage on site? Because whichever team or group is responsible for doing this, they will be on board and supporting this directive. Nationally, in South Africa, There's the National Water Resource Strategy, NWRS3, Sustainable Development Goals. There are site utilities budgets set aside to help sustainable projects like this. We have to consider environmental protection. By that, what I mean is that if water is coming into a chemistry, pharmaceutical, plastics, agrochemical site, it potentially may become contaminated and will need to be cleaned before being put back into the system. If we're using a closed loop circulator system, then we are not contaminating running water which is being consumed and then removed from the site. So we're improving our environmental protection and improving site safety as a whole. How much water are we actually talking about? Well, we did some studies, and typically one tap in the laboratory will consume approximately 2.5 litres per minute. It'll be delivering 2.5 litres per minute. That equates to approximately 150 litres an hour, which in an 8-hour day is around 1,200 litres for an 8-hour day. And that's assuming that the user is turning the tap off when they go home. Very often they may not do. They may forget, and the tap is just running 24 hours a day. Taking that as the exception, if we were running 8 hours a day, 5 days a week, 50 weeks of the year, that would estimate at about 300,000 litres per year, per tap, which is a considerable amount. So we spoke with a number of different companies, and there was a company in the UK that we spoke to, and that had a small lab condensers similar to those that we see pictured here. And there were approximately 50 chemists in this laboratory who collectively were using around 10 million litres of water per year, approximately 200,000 litres per chemist, which sound crazy numbers. But we'd suggest that you maybe take a look, and if you haven't measured how much water you're using, perhaps measure it. See how much water is being consumed by your tap, by a condenser, if it's just running down the drain. Now, how much does that cost? What's the implication for the price? We can only talk here about what might be in the UK, different countries, different states, particularly in South Africa, for example. It will depend on what is the nature of the company that you are working with, who is your water supplier, what deals have been worked out, what government incentives there are, and so on. But to give an illustration, water supply means that we need to pay for the water coming on site, and more importantly, depending on the function of the site, pay for it to be cleaned before it goes back into the general system in the country. And approximately that 43,000 per year is around 1 million South African rand. So then we very often get the question, what is the payback and what can we use? So we have a variety of different machines available, going from small 250 watt cooling machines that could be suitable for 1 or 2 rotary evaporators, for example. Or you may choose one machine to connect to 4 systems, 6 or 8, so that there's one chiller providing the cooling for multiple units. And our representatives at Lasec are well trained at being able to offer site assessments of what might be the most cost-effective way to move to a closed-loop water supply system. If there are bigger applications, we mentioned before about the spectrophotometers, the larger scale rotary evaporators, 50 litre, 100 litre, or for example, maybe a more kilo lab or maybe even plant size cooling, where we require 10, 20. At LAUDA, we offer cooling systems going up to 250 kilowatt cooling supply. What's the return on investment? Now, this very much depends on how much you're currently using and what you're currently spending. So we can't give you exact figures. That's a calculation that we'd need to sit down with you and help you calculate for yourselves. But typically in Europe, in a standard typical laboratory, a microcool 250, the payback time is within about 18 months, using one microcool to cool one rotary evaporator. If we move to a larger system and we have, for example, a UC2, an ultracool 2, which would have 2 kilowatts cooling, we expect that would pay for itself in under 12 months. And the larger we go, when we go to the UC8, 8 kilowatts cooling, we're looking at somewhere around 6 to 8 months payback time. So whilst it does depend very much on what we're replacing and the demand we're replacing and the specifics of your own supply, we see a trend that the larger, more powerful machine will pay for itself in a shorter time period. However, we may say, if we have a large machine, isn't it going to be noisy in the lab and generate heat that's going to put an impact on our HVAC system, the heating, ventilation and air conditioning system? If we're filling the lab with chillers, that heat has to go somewhere. Where's it going to go? Well, if they're inside the laboratory, yes, they'll go into the HVAC system and the HVAC system will have to handle it. Which is why at LAUDA, our ultracool systems are designed with a weatherproof Ep.5 casing, designed to go outside the building. They will run in ambient temperatures from -15 centigrade to +50. They're equipped with higher pressure pumps to be able to supply cooling main systems. And in that way, any heat that's generated by the chiller is automatically vented into the atmosphere outside rather than putting a heat load on the HVAC system. Because ultimately, the HVAC system would then generate more heat, trying to remove that heat. So venting it straight into the air is a much better way of removing that heat from laboratory applications. And they can be set up on ring mains, piped through the wall. And we would expect that some local contractor would be able to do that. And our team at Lasec will be able to consult as to what is the most appropriate system to use, where to put it, how close it should be. So what are the next steps? Well, I mentioned earlier about measure how much water is being consumed. You may have that for a site consumption, but what about for yourselves in the laboratory? Maybe take a 1 litre flask, put it on the drain of one of the tap water systems and see how quickly it's filled. Get a litres per minute per tap, multiply by the number of taps, and estimate what is the annual approximate usage, the cost for your laboratory, for your department, and for your company. Now, that may be too much of a project for one person in the lab, but there are companies, people within the company who are able to offer and support with that. So identify who is the person responsible for site water consumption and sewage. What is the site usage? What is going down the drain? What is having to be cleaned? Try to understand who in your company writes the sustainability policy. Does the company have a water sustainability statement? How can you as an individual help your company achieve its goals for water sustainability? Is there a budget for long-term investment that could be used for investing in chillers for your laboratory so that it doesn't come from your own equipment budget, but comes from a wider site budget? And as I mentioned before, the Lasec representative is on hand, available to come and visit to give an on-site assessment and to explain how LAUDA and Lasec can help you meet sustainability targets.
Thank you so much, Steve. That was really, really insightful. And thank you for everyone who's attended. Really appreciate your time and your your attention to what was being shared. Like Steve said, if we have not answered any of your questions, we will reach out and answer them within the next week. Enjoy the rest of your day further. Thanks.
Thank you, everybody, for your time and your attention. And thank you, Tamryn and the Lasec team, for inviting me and putting the sustainability program together.